Wanted to work a problem that involves the Rutherford atom. This is a simple model of the atom. It's a classical model of the atom where the atom is like a solar system. In the atom, the electron orbits the nucleus of the atom, like the planet Earth orbits the sun in the solar system. So in this question, we're asked to imagine a classical Rutherford atom in which an electron is orbiting a proton at a distance of 1 times 10 to the minus 10 meters. So that's 1 angstrom distance, or a 0.1 nanometer distance. And based on that, we're going to calculate the speed of the electron in this orbit and answer the question whether relativity is going to be important or unimportant. And then secondly, we're going to calculate the wavelength of this electron, and we're going to answer the question of whether wave-particle duality is important. And so let's go ahead and do those two things. We'll first calculate the speed of the electron in this Rutherford atom. We'll then calculate the wavelength of the electron in this Rutherford atom. So in the atom, the electron orbits the proton, as depicted here, and the electrical force is providing the centripetal force for this orbital motion. So the basic idea is that the centripetal force Fc is equal to the electrical force Fe. So I'm going to use that as the starting point for calculating the velocity of the electron at a radius of 0.1 nanometers. So Fc equals Fg, E. Now, the centripetal force depends on the speed of the orbital motion and the radius of the orbital motion. It's mv squared over r. The electrical force depends on the product of the two charges. The two charges of the electron and the proton both have magnitudes of the electronic charge. So we're going to get an E squared divided by the distance squared between the proton and the electron. That's the radius of our atom, multiplied by the Coulomb constant, K. One comment here is, I'm just thinking about the magnitudes of the centripetal and electrical forces. I'm just filling in the magnitudes of the two forces. I'm not worried here about the signs or the directions of the forces. And if I take this equation, I can rearrange this equation as an equation for the velocity of the electron. So if I multiply through by the mass, divide through by the radius, and take the square root, I get the following equation. For the velocity. So filling in the values of the various quantities, we got the Coulomb constant. That's 9 times 10 to the 9 Newton meters squared over Coulomb squared. We've got the electronic charges of the proton and the electron. That's 1.6 times 10 to the minus 19. We've got a squared. We've got the mass of the electron. That's 9.1 times 10 to the minus 31 kilograms. And finally, we've got the radius of the electron, the radius of the atom. That's 1 times 10 to the minus 10 meters. And if we carry out this calculation, the speed that I got was 1.6 times 10 to the 6 meters per second. And if you think about that speed is less than 1% of the speed of light. So in answering the question whether relativity is important or unimportant, I would say that relativity is unimportant, maybe a small correction. So we don't need to worry too much about relativity in our Rutherford atom. And now let's take the second question. The second question is, what is the wavelength of the electron in the atom? And so we're going to use the equation for the de Broglie wavelength for the electron. That's the matter wavelength of the electron. It's Planck's constant divided by the momentum of the particle, the momentum of the electron here. Here we're going to fill in the momentum in terms of the mass of the electron and the velocity of the electron. And now again, we just got to fill in the various numbers of the quantities in our equation to calculate the wavelength. So I've got Planck's constant at 6.6 times 10 to the minus 34 joules seconds. And we're going to divide that by the product of the mass of the electron, 9.1 times 10 to the minus 31 kilograms. Times the speed of the electron, which we just calculated, is 1.6 million meters per second. And I've already calculated this quantity here, so let me just write that down. I got a wavelength that is 0.45 nanometers, or 4.5 times 10 to the minus 10 meters. So in this case, clearly the wave nature of the electron is going to be important, because the wave nature of the electron is the same size scale as the atom itself. Anyway, that was an example of the Rutherford atom. It's a classical atom in which an electron orbits a nucleus like the Earth orbits the Sun. It's the electrical force rather than the gravitational force that's providing the centripetal force to maintain the orbit. And based on that model of the atom, we are able to investigate whether relativity would be important in the atom, not very important, and whether the wave nature of electrons would be important in the atom. That seems like that would be very important.